All right. Wonderful. So before I just get started, how many people here know what Kafka is? Okay. I will try to give a little bit of intro for the rest of you. So very briefly, who am I? I am a staff site reliability engineer at LinkedIn. For about 4.5 years, I worked on Apache Kafka. For the last year, I've been doing something a little different in the capacity engineering space. But from 2013 through last year, I was building Kafka at LinkedIn. And as you may have heard this morning, if you were in the intro talk, we have one of the largest Kafka deployments. We actually invented Kafka and then contributed it to Apache. I've also co-authored with Gwen Shapira the definitive guide for Kafka from O'Reilly. So if you want to help me out, buy my book. Always have to pimp that in here. And I used to be with VeriSign Infrastructure Engineering before that for 10 years in the DC area, building the infrastructure that resolves common net DNS for everyone. So what I'm not going to do today is I'm not going to tell you what Kafka is. I'm not going to go into a lot of introductory material on Kafka. For those who don't know, it is a streaming data platform, publish subscribe messaging system. As it was described this morning, it's essentially a distributed commit log, and you can do lots of things on top of that. I'm also not going to give you an encyclopedia of what monitoring is. I have a whole nother talk. If you're interested in hearing that one, I'll be at SREcon in Asia, in Singapore, in June, talking about monitoring and all the wonderful things you can do in monitoring, and all the ways you can mess up your own life by doing it wrong. And I'm not going to talk about automation around Kafka. I will touch on some tools at the end, but there's a lot of stuff out there to do. What I am going to talk about is monitoring for Kafka specifically, and why everything I said for 4.5 years is pretty much exactly wrong, and what we've learned over time, how we've learned to do it a little bit better. So at LinkedIn, we have a process called Code Yellow. Code Yellow is for engineering teams that have gotten themselves into a lot of trouble. Usually they have capacity problems, they have high toil. Toil is defined as work that you shouldn't be doing because the computer can do it for you. Maybe you have communication problems. So at the end of 2017, moving into the beginning of 2018, last year, Kafka was in this space. Kafka at LinkedIn was in Code Yellow. And this talk was born out of what we were doing at the time with the Code Yellow and all the things we learned. So why were we in Code Yellow? If you're in operations at all, graphs like this haunt your nightmares. So back in 2010, we invented Kafka. We were doing no traffic at the time. So we started using Kafka within LinkedIn. And then right around here, towards the end of 2015, we hit 1 trillion messages a day through Kafka at LinkedIn. We had a little party, we celebrated, it was great. Little over a year, almost 2 years later, we hit 2 trillion messages a day. Hey, we had another big party, this is great. We're really using Kafka well at LinkedIn. So that was in mid-2017. By the end of 2017, at the end of the year, we were at 3 trillion messages a day. And now you see where my problem comes in, because 3 months later, in March of 2018, we were at 5 trillion messages a day. Something happened the end of the year that we weren't expecting. There were a number of things that happened here, and we found ourselves in a big problem because our alerts were going off constantly. I was on call for a week at one point, thankfully only 12 hours during the daytime. My phone was going off on the clock about every 3.5 minutes with a paging alert. 90% of them were not actionable. 90% of them I couldn't do anything with. I just ignored them because I knew what they were, or they were a bad alert, or there was some other problem. So we were in a really bad spot because of this. So I'm going to talk a little bit about what we were doing wrong, and then some of the things that we're doing right now. So monitoring is not the same thing as alerting. When you're monitoring, you're collecting everything about your system. If you've run Kafka, you know that Kafka emits thousands upon thousands of metrics via JMX. If you're running mirror makers to mirror Kafka, you've got lots and more metrics. You've got operating system metrics. You've got everything going on in your system. You want to alert on almost none of these. Most of them are not useful when it comes to telling you what's going on with your system. They're incredibly useful if you want to debug what's going on later. Events are better than metrics, so nice wide events that have lots of information about their context are always going to be better than single numbers. They will tell you more about what's going on in your system. And tests are even better than that. This is what we call moving things to the left. So if you think about your continuous integration pipeline as a pipeline moving from the left to the right, the more you can move things to the left, the more you can move things earlier in your pipeline and catch them earlier, the happier you're going to be at the end of the day. Because at the end of the day, really all you want to do is sleep at night. You don't want your phone going off. You don't want to have to wake up at 2 o'clock in the morning and then work until 8 a.m. and then feel bad because you're not going to go into work until 10 a.m. and then, if you're lucky, have your boss tell you to go home because you're falling asleep at your desk. So the best thing to focus on when you're monitoring is service level objectives. Very briefly, do not call these SLAs, please. SLAs are service level agreements. SLAs contain service level objectives. They also include penalties for what happens when you don't meet your service level objective. So your objective is the thing that you want to hit. You have an indicator, an SLI, which is a metric. You have a threshold, that is your SLO, so now your threshold on the metric. And then if you don't meet that threshold, then you have a penalty. For example, at VeriSign, if the .com, .net DNS name servers ever went down, we were going to be paying ICANN, the large organization across many countries that runs DNS and numbers. We're going to be paying them $1 million a day. That's an SLA. I don't have SLAs for my internal customers for Kafka. I have SLOs, and if I fail to meet my SLOs, then we have an incident and a postmortem, and I say, I'm so sorry, and go back to doing my job. I don't pull out my wallet and fork over cash to them. So SLOs around services usually revolve around availability, latency, and whatever guarantees you're giving to your customers. Most of them are around availability and latency. Your customers want to know that your service is up and running properly and that it's responding in a reasonable amount of time. Now, you may have other SLOs that you're going to work with around correctness or anything else that you promise a customer. It's all about what you promise a customer. So I'm going to get back into SLOs a little bit later in this talk because this is doing it right. So let's talk about the 3 metrics that I promised you in the title of the talk. What are the key Kafka metrics that you want to work with? The first one is URP, under-replicated partitions. If you were in Sven's talk this morning, Intro to Apache Kafka, you heard him talk about partitioning. So under-replicated partitions are partitions where one of the replicas in the partition has gone down. It's not fully online. Request handlers are the next one I'm going to talk about. These are the thread pools within Kafka that do the actual work. And the last one I'll talk about is request timing. This looks like latency. It's not really latency. It's close, but not quite there. So let's talk about under-replicated partitions. We've talked about this a lot. In fact, I actually wrote significantly about it in the book, about how great under-replicated partitions are and how we can use them for telling us about all kinds of problems. They give you information about the overall cluster health, and because they are a core part of Kafka, they are both a consumer of data and a producer of data. They can actually give you some indications about problems that your clients are having as well. So if we look at this graph here, this is an example of a broker that's gone down. So you have, in this cluster, looking at the number of lines there, let's say we have 20 brokers. One of the brokers has gone down. Now all of the partitions that were on that broker are under-replicated. So all the other brokers in the cluster have some count of partitions that are under-replicated because of that broker that's down. Okay, great. This is a pretty clear graph. It's not too bad. Here's one where we have one broker, one color means one broker, that has a variable amount of under-replicated partitions all the time. It's not consistent. This tends to indicate a problem with the consumer, so that broker is having a problem consuming data from other brokers. I don't really know where the problem is without digging into this further and going into a lot of debugging on it. This is a very pretty graph. I actually have no idea what this graph means, but I've seen it several times before, as evidenced by the fact that I copied it off of our graphing system. This could indicate a producer problem. So there might be one broker that's being slow, and all of these other brokers are having problems producing to that broker via the internal replication. It could also indicate a lot of other problems. Like this here, this is kind of weird here at the end. I don't know what happened there at all. So what do we say about under-replicated partitions? What do we say now? Okay, I won't spoil anything by just saying not today. They are overrated. For years, I touted under-replicated partitions as the one true way to monitor your Kafka cluster. The problem is that it doesn't map to an SLO. Your customers don't care if the partitions are not fully replicated within the cluster. You might care because it means you may be in danger of having a partition go offline if you lose another broker, but it doesn't impact your customers at all. They can still write. They're often not actionable. You frequently can't do anything about under-replicated partitions. For example, if I'm moving a partition within the cluster because I'm rebalancing traffic, then that partition is under-replicated by definition while I'm moving it. I can't do anything about that. It's just going to be an alert that goes off and doesn't give me any useful information. This is one of these metrics that I now say you should collect but not alert on. It is useful to give you information about the state of your system, but if you alert on it, you're just going to be waking yourself up for absolutely no reason. Now, my co-author of the book, Gwen Shapira at Confluent, will disagree with me vehemently about this, and I like that about her because we will argue about this. At the end of the day, I'm right and she's wrong. And that's just the way I'm going to call it. She'll tell you the exact opposite. So let's move on. We don't like under-replicated partitions. So let's talk about the thread pools. Kafka has lots and lots of thread pools. There is a network thread pool. There's a request thread pool. There's a log cleaner thread pool. I think there's probably 5 or 6 thread pools within the Kafka broker that do work. The only one that I really care about is the request handler. So the request handler is responsible for doing all the work for client requests. It decodes and validates the messages, it performs the work that has to happen, it waits for answers from other brokers, and it assembles the response. There's another thread, the network handler thread, that is actually responsible for talking to the client. So it receives the request from the client, and then once the request handler is done with all its work, it sends the response to the client, but it's not otherwise involved in the work that's going on. So the request handlers are very interesting to us because there's lots of work going on with a Kafka request, whether it's produce or consume. You can have lots of different problems with the request handlers. The 3 main categories I have here, CPU time, timeout, and deadlock, are all ones that I've seen frequently. So CPU time is you're spending lots of time when you're doing the request handler. So if you're spending too much time, you're going to exhaust your request handlers very quickly. You'll see problems here with disk I/O, because disk I/O is counted in CPU time. You'll also see problems with SSL and compression that's going on within the brokers. Both of those take up a lot of CPU time, and they can tend to cause issues. Timeouts and deadlocks look very similar. Timeouts are really when the request handler is failing because it's waiting for something to happen. It eventually times out and it moves on. Deadlock is even worse because deadlock means that it's waiting for something to happen that is never going to happen by definition. So I got one graph here. This is actually a healthy broker. There's no problem here. I didn't do anything about this. What was happening here, let's see. Oh, good, my green does work. So what's happening here is we're shutting down brokers and restarting them. This is a rolling restart of the cluster. So as we shut down the broker, all the request handlers time out, and then it restarts and it goes back to normal. Once you're done, everything's good. You might see why I don't really like these for alerting either. Again, there's nothing wrong here. There's nothing going on. Now, this could be a problem in another situation, but in this case, I was restarting the brokers. I knew exactly what was happening. So these timeouts were okay. Deadlocks are much harder. Hopefully, you never run into a deadlock in Kafka. It's coded very well. Yes, it's coded very well. I can say that with a straight face because I don't write the code for Kafka. You're going to run into these if there's a software bug. In general, you're not going to see them. If you do see them, please, I hope you have support from someone else, because trying to get into the internals of Kafka is complicated even for people who have been working with it for years and years. It works so well because the internals are so complex. But they're going to look just like timeouts, so you're not going to know what you're looking at unless it doesn't recover. So you might say, if you know something about Kafka, wait a minute, the brokers don't do compression. The clients do compression, and then the broker just writes it to disk. We fixed that. We fixed that like 3 or 4 years ago. And that's absolutely true. The brokers shouldn't do compression at all. But there are several situations where they do, and they will surprise you when they happen. The two situations are called up conversion and down conversion. Up conversion happens when the brokers are running a new version of Kafka, your clients are running an old version of Kafka, and you've changed the format of the messages on disk within Kafka. So when you upgrade Kafka, you can keep the message format as the old format, or you can move to the new format. If you move to the new format too quickly, then what happens is when your old clients send data to Kafka, the broker has to convert the messages to the new format before it writes them to disk. In doing this, it decompresses the message, it finds out they're the old format, it converts them to the new format, then it recompresses the message and writes them to disk. Now your broker's doing compression. This is a bad thing. You don't ever want this to happen. The other one is down conversion. Your Kafka brokers are running a new version. You have not upgraded the message format on disk because you're smart and you knew you shouldn't do that before you upgrade all your clients. Then you upgrade all your clients. Your clients now support the new produce format. So they send messages to the broker in the new produce format. The broker decompresses them, sees that they're in the new produce format. It needs to write them in the old format, so it down converts them to the old format, compresses them, and writes them to disk. Now you've got a new problem. You're still compressing data. This is part of what makes upgrades in Kafka really, really difficult to deal with. You've essentially got a race condition here. You can either upgrade all your clients, or you can upgrade your message format, but one way or another, you're going to be doing compression for a while. So you have to watch out for these. These are going to eat up CPU time. These are going to eat up request handlers. I'm going to stop here for just a sec. Caveat. I stopped running Kafka a year ago at LinkedIn. I started doing something else. A year ago, we were still running 0.11. We are now running 2.0. We're running 0.11 with some stuff backported. Most things have not changed within the Kafka broker significantly in that time. All of the monitoring information, all the request handler information, everything still applies. There are changes to the controller and other things under the covers that may not apply 100% anymore. So take what I say with a grain of salt. Most of it works. But for example, up conversion and down conversion, to solve this at LinkedIn, we added a custom parameter to the brokers where we could lock the API versions at the broker. So if a producer asked the broker what versions of the message format it supported, it would give a limited answer back so that we wouldn't run into the down conversion problem while we were doing upgrades. I don't believe that made it into Kafka open source, but I could be wrong. If it did, then, okay, good. I'm going to look at Sven every time I have a question over here. So that will help with down conversion. This is a major problem. And honestly, a year and a half ago, when I would talk with other people at Confluent, other developers about it, they would say, no, that problem doesn't exist at all. That doesn't happen. And we would sit there and I would explain and say, this is exactly how it happened. They're like, oh yeah, that can happen, but it shouldn't happen that often. When you're running 5 trillion messages a day through a system, things that don't happen that often happen every day. It's just the way it works. Disks fail constantly. Systems fail constantly. We run into every single bug that shouldn't exist in the system. Okay, so request timing. We don't like the request handlers either because we can't use those. So let's move on to request timing. Request timing is great. Now we're talking about latency. So request timing within Kafka, the broker exposes a bunch of metrics about the timing of each request. So the 6 are up here. You have the total time, which is the amount of time end-to-end that processing the request takes within the request handler. It doesn't include network time. You have the request queue time, so the amount of time the request spent waiting to process before it could get handled by a request handler. The local time, which is the amount of time the broker that the request is being processed on took on that broker. Remote time is the amount of time that request spent waiting for other brokers to give an answer. So if you were in the talk this morning and AX all was mentioned, AX -1, where you produce a message and wait for a response from all brokers, that's spent in remote time. Response queue, which is the amount of time that the request handler waits to send the request back to the network handler so it can send it back out. And then the response send time, which is the amount of time to send it to the client, which is actually just the amount of time it takes to dump it to the network. It's not the full amount of time that it might take the client to get the response. So we've got lots of great numbers to work with. So let's see what we can use. So this is produce total time. What's really difficult to see here is that these graphs are at the same scale except for 3 orders of magnitude. This graph over here is from 0 to 8.5. This graph over here is from 0 to 9,000. And this is measured in milliseconds. So what's the problem here? This is a healthy broker. These are 2 graphs from a healthy broker. This is, I believe, the median time I pulled, and this is the 99th percentile produce time. Okay, why is there so much difference between produce local time and produce total time between the median and the 99th percentile? The problem is that every produce request is not made the same. I can produce 5 bytes to the broker, or I can produce 1 megabyte to the broker. Those will take different amounts of time to process. There's also several other things that we'll get into in a sec that could come into play here. So if we can't really look at the total time, what can we try? Well, let's look at the local time. I mean, right, the work that has to happen on the broker itself has to be pretty similar, so maybe we can use that. So again, this graph goes from 0 to 1. It goes up and down like that because you don't tend to measure in a granularity less than 1 millisecond very often. And this one goes from 0 to 2600. Again, median graph, 99th percentile graph. Okay, why does the local times take so much difference? Again, takes a different amount of time to write to disk. Writing 5 bytes to disk takes a lot less time than writing a megabyte to disk. So we can't use this one either. This doesn't really give us much to go on. It's too difficult to baseline. I can't alert on 1 millisecond. It goes from 0 to 1. The only reason it does anything in between is because it averages over the window of when your metrics are going out. And this, I can't baseline at all. I mean, I can't really find a good answer in here for where my alert should be. Maybe it should be at 3,000, but what if I get a larger request that comes in that takes longer to process? Okay, can't use local time. We're going to set that aside. Let's look at remote time. I mean, if you ask another broker for an answer and come back, that should be pretty similar, shouldn't it? 0 to 2, 0 to about 4,000. Okay, again, I can't use these. Why are these different? This one, in the median case, we're probably producing with AX1, where we don't ask any other broker for an answer. So there is no remote time. The remote time is essentially instantaneous. This one, the 99th percentile, is probably requests that are being produced with AX-1 or AX-all, which means we're waiting for at least 1, possibly more brokers to send a response back. The way Kafka does this internally means it takes a long time, because what actually has to happen is the remote broker has to fetch the messages, and then it has to fetch again to indicate that it's received all the messages. It takes 2 round trips at least for this to happen. So I can't use this either. Again, I have a problem baselining these numbers. I can't tell what's going on inside the broker just from looking at these numbers. So that's great. Gave you my 3 metrics. You're all set, right? You know how to monitor Kafka badly? I can go away now? No. Okay. So what do you need to know? What do you actually want to monitor if you can't use any of these metrics out of Kafka to do it? We're going to come back to the SLOs here. So what you really want to do is you want to monitor Kafka externally. If you rely on Kafka itself, the broker itself, to tell you what's going on, you'll never actually know what's true about your system because you're just asking the system to monitor itself. If I ask Kafka itself to tell me what its availability is, it's going to say, I'm up, everything's good, 100% available. The network cable's cut, but I'm up and running just fine. There's no problem here. So external monitoring tells you what your clients see, and that's what you want to alert on. I'm going to mention this tomorrow when I'm downstairs talking about site reliability engineering. And if you want to know what site reliability engineering actually is, I encourage you to come to the talk tomorrow at 10:30 on the Devtrends Stage, and I'll be going into detail on that. But the only thing I care about when I'm monitoring are the things I don't know about. If I know about a situation, I can automate that, and I don't need to alert on it. I don't need to worry about it at all. I want to know about the things that I don't know about. The only way to know about things that I can't monitor directly is to monitor what the client sees. If the availability drops or the latency drops and latency goes up over the SLO, then I know that there's a problem I need to go look at. I don't know what the problem is, but I know that there's a problem, and that's what I want my alerting to tell me. So one way to do external monitoring of Kafka is using this tool that we developed called Kafka Monitor. And it is open source. It's on our GitHub. What Kafka Monitor does is it's an application that sits outside of your Kafka cluster, and it produces messages in, and it consumes them out. And there are several other tools like this. I know that Confluent has their own tool. There's probably a couple others who have developed similar tools as well. This one's ours. Since it's ours, it's the best one out there. So it will measure the availability of your system as your clients see it, because it is a client. It is consuming and producing messages. It will also measure the latency, so it knows when it produced the message, and when it consumes the message, it can tell you how long everything took. This is what a client cares about. The client cares about how long did it take me to produce the message end to end? How long did it take me to consume the message? How long was it before a message that I produced was able to be consumed? It doesn't care about, clients don't care about what's going on inside the system. They only care about the outside of the system. They care about the interfaces. So this is what you need to care about as someone who runs Kafka. So this is good. This will actually get you a long way towards monitoring Kafka the right way. And if I could convince all of my colleagues at LinkedIn to actually do this, we would be in a much happier place. We have shifted towards this way, but what you will find, especially moving towards SLO-based alerts, is that institutional inertia will tell your operations folks that they can't cut back the number of alerts, that they have to keep adding more alerts to tell them about the problems, and they can't trim themselves back to just knowing when there's a customer-facing problem. A good example of this is when we had a file descriptor leak within Kafka. So we ran into a situation where Kafka was leaking sockets. It wasn't closing them properly. And what happened was the application would run out of file handles all of a sudden and crash. Okay, we don't quite know what the problem is, so we added an alert for file handle utilization. So we cranked up the number of file handles that were available to an obscenely high number, and we added an alert at about 50%. So the hope was that we could catch it while this was going up and out of control, restart the broker before it crashed and caused problems. That's fine when you're actively triaging an incident. Then we found the problem. We found the 2 or 3 lines of code that were wrong within the Kafka broker and fixed them and rolled that out, and everything was fine. No more file descriptor leaks. We still have the alert. The alert's still there because, well, what if it happens again? Well, this is where we move things to the left. Well, if it happens again, we should catch that in a test. We should test when we compile the code whether or not it is leaking file handles. That's something that we can check for. And at the end of the day, what ended up happening was everything was fine. This alert never fired because we had 800,000 file handles available to Kafka, and it never went over 20 or 30% of that. And then one day it fired. And it fired because there was natural growth in the cluster and the limit needed to be bumped up higher. It wasn't a problem. The alert just went off spuriously. It could have been handled 3 days later. It could have been handled 2 weeks later, and it would have been fine. There wouldn't have been a problem at all. But yet we have this alert hanging around that nobody needs, and nobody wants to get rid of it because it might happen again. There are lots of things that might happen again. My SLO alerts will tell me when they actually do happen. All right, operating system and hardware metrics. These are lots of the other metrics that you have. Things like CPU utilization, disk I/O, memory usage, all of these things that kind of come with your system for free. The biggest problem is, what do they mean? So CPU load is a great example of this. You get lots of operations people who alert on CPU load. Nobody actually knows what CPU load is. I guarantee, okay, does anyone actually know the calculation for CPU load? My point exactly. CPU load is essentially a percentage utilization of the system. You take the number of processes that are in the running state and the number of processes that are in the blocked state and the number of CPUs, or the number of cores you have, and you do some black magic and everything works and you get a number out the end. So we don't really know what it means. We also don't know when we're alerting on CPU load why the CPU load is high. We don't even know if it's okay that it's high. What's high? If you've got 32 cores in your system, then 32 is high. If you've got 12 cores in your system, then 12 is high. There's no good information there. So with all of these metrics, and really with every metric, don't alert on it unless you have a 100% clear signal what is wrong, and you have a 100% clear response to that. The one exception to clear response is the SLO alerts. Those indicate something where you know that there's a problem, you don't know what it is, but you know you have to fix it. So don't use these. These won't help you. If your system is down, that is a clear alert. That is a clear response. Get the system back up or replace it. But past that, most of these are useless. Capacity planning. I just mentioned all the operating system and hardware metrics, and you say, well, wait, I got to know when I'm running out of disk. I got to know when I'm running out of CPU. Yes, you do. You should plan all of these in advance. These often are calculations on multiple metrics. So you need to figure out where your bottleneck is and measure your bottleneck, and you need to track your disk usage. Don't alert on any of these. Do not alert on disk utilization. I know there's probably a number of people who are running systems who say that's crazy talk. Why don't you alert on capacity metrics? You are not a magician. You cannot turn around at 3 a.m. and pull a 2U rack server out of thin air to throw in and take care of your capacity problem. You have to have ordered those in advance. So they have to be sitting there in your data center. And if they're sitting there in your data center, then why haven't you installed them already? There's no use in having hardware sitting there doing nothing. So these are not things that you can act on in the middle of the night, so you don't need an alert going off to tell you that you need to do something about them. Some of the metrics you're going to look at for capacity long-term, the request handler idle ratio is a great one. So this is a Kafka metric. In general, I've found that if the idle ratio, so this is the percentage of request handler threads that are not in use at any given point in time. If that drops below 20%, you're going to have problems with your Kafka cluster. It's not 0, it's 20%. Anything below 20% starts to break things. You start to have problems. Disk utilization is a great one. Partition count within Kafka is another good one to track long-term for capacity, because the way Kafka works, there are actually some limits with the way it will scale horizontally within a single cluster. You start getting up to high partition counts, either for a single broker or for a cluster, you're going to have a lot of problems. I won't even bother going into what high is here. If you want to talk to me about that, we can talk later. Network utilization is another one. If you saturate your network interfaces, you're going to be a very sad person. So these are the metrics that you really want to look at. You want to look at your external monitoring. You want to track capacity long term. You don't want to wake yourself up with any of these things. So if I leave you with nothing else, define what your SLOs are. Define your customer expectations. Not only will you be happier when you know what to alert on, your customers will be happier when they know what to expect. Monitor those SLOs, preferably externally. And any metric that covers lots and lots of problems, that tells you about lots and lots of different things, is noisy and useless, and you should never use it. Collect it, look at it later, but don't bother alerting on it if it tells you about too many things. And buy my book. This presentation, this slide deck, is posted on SlideShare, so you can download it from there. Just slideshare.com/Todd Palino is all my stuff, and this one's on there. There's some links for useful things. Kafka Monitor, Burrow, which I didn't go into here, but Burrow is an application that I wrote for monitoring consumers within Kafka. I'm not actively maintaining it right now, but there are other people who are actively working on it in open source, so it has good support, and there's a lot of people using this. Cruise Control is a tool that we wrote within LinkedIn for rebalancing Kafka clusters and handling brokers up and brokers down. Kafka Tools is another set of Python tools for doing some things like that. And then there's information about the Kafka community so that you can get yourself involved there. And with that, I actually am done. I don't know if I have. There's like a minute and a half for questions right now. If somebody does have
even
one.
more,
Okay.
because like your time is until 1:30. So
Okay, we started a little early, so I got about 10 minutes for questions if anyone does have any.
They look
questions.
shy. So.
No questions. I must have done the best job ever telling you about Kafka monitoring. If you do come up with some, I'll be around. Again, I will be downstairs on the Devtrends Stage at 10:30 tomorrow to talk about site reliability engineering. So thank you very much.
Thank you.